Right. So, yeah, so I'm looking at the impact of sea ice loss in a very specific region just over the British Isles. And this is kind of insights from something we might be able to do with the Polar Amplification Model Intercomparison Project's data. So just to give you a really quick summary of what that is, that's these atmosphere-only simulations which either simulate low sea ice or increased SSTs. So when you lose the sea ice, you get this Arctic amplification sort of thing. And if you increase the SSTs outside of the Arctic while keeping the ice constant, you get sort of tropical amplification. The idea behind this is to try and understand some of the consequences of the Arctic amplification we've observed. So yeah, just a quick idea on the theory here. We have sea ice loss driving Arctic amplification, which weakens the equator to pole temperature gradient. And then that, through the thermal wind equation, would shift the jet equatorward, weaken the jet, and weaken the storm tracks. And that's kind of shown in this, this schematic on the left here. Left-hand side shows kind of a past cold climate, and the right is a warmer climate. And you get this weakening of the storm tracks and this shift in the jet. What's somewhat more hypothetical part of this link would be then that you'd have a weaker jet, which might be wavier, and a wavier jet would have large meridional excursions, and that can foster the kind of conditions needed to have extreme persistent weather in the mid-latitudes. But this has turned out to be, quite the topic of interest of the last 15 years. There's just been tons and tons of papers that have come out looking at this sort of thing. And so one of the goals of CMIP was to really get into this at a multi-model kind of perspective. And part of it is that on its own, or in reality, sea ice loss doesn't occur in isolation. So this schematic here is showing what I just said. You have changes to the northern hemisphere cryosphere, which causes Arctic amplification, which would cause changes in the storm tracks and the jet stream and waves, which impacts mid-latitude weather in the northern hemisphere. But at the same time, you have global climate change occurring. And in particular, you have tropical amplification. So what I'm showing here is this idea that certain forcings and certain feedbacks might create more tropical amplification or Arctic amplification. So these feedbacks are the ones that are below the line show ones that would favor tropical amplification over Arctic amplification. And what you then get is this alteration of the temperature gradient that doesn't just occur due to Arctic amplification, but also due to warming in the tropics. And so you get a weakening of the gradient at the surface and then a strengthening aloft. And so this gets this tug-of-war idea between the high and low latitudes. And that was shown really nicely by this paper by Butler et al. 2010 in an idealized model. This is the eddy momentum flux that would decrease in the middle latitudes when you have Arctic amplification, or this eddy momentum flux that would increase if you have tropical amplification. But just to go talk quickly about a paper that I have that's coming out quite soon, it turns out that in reality it's not quite so simple. We do get sea ice loss, weakening the temperature gradient in the mid-latitudes, but if you separate it into the Pacific and the Atlantic, you can see that it looks about the same in both, but what's different is if you look at what happens in response to ocean warming. And so if I draw these lines here, you can see that in the Atlantic on the right-hand side, they're opposing each other, but actually in the Pacific, they're enhancing each other. So this is sort of a situation that's really kind of unique to the Atlantic region and not so much in the Pacific. Really briefly, why we have a different situation in the Pacific has to do with the existence of the continents kind of creating this warming to the north of the basin, and actually in particular are warming along the North American mountains, so like a snow albedo feedback that's itself driven by ocean warming rather than by polar forcing. So this idea that there's a tug of war is quite unique to the Atlantic. But this has really important implications for how projections of European climate can be understood. So we can separate them into a response to sea ice loss and a response to ocean warming. But these relative magnitudes are also quite important. So we need to consider the storylines of climate change to understand the possible range of projections we can be looking at. Okay, then to get to the actual part of my talk that's relevant. So what does this mean for winter weather in the British Isles? And just to specify, I'm talking about the winter because I had a paper previously looking at PMIP that showed that in the summertime, there was really little impact of sea ice loss on the storm tracks. So we're just ignoring summer completely. I use up to 13 models, which have between 100 and 300 ensemble members. and 3 experiments. There's a control experiment, one with low sea ice and one with higher SSTs. These are all AMIP style, 14-month long, forced with annual cycle of SSTs or sea ice. And I'll just briefly go over this part. We kind of start at large scales. We try to look at the large scale, variability of the North Atlantic. Then we look at the North Atlantic storm track. Especially we want to look at the storms that would track within the British Isles region, and especially the strong storms that do so. And then we try and look at some kind of more local changes to temperature, precipitation, and especially extremes in those things. So moving on, first we looked at EOFs of North Atlantic monthly sea level pressure. This is an ensemble mean of all the models that participated in PAMIP. And you have the first 3 modes of variability, which are the NAO, the East Atlantic pattern, and the Scandinavian pattern. And together they explain 87% of the variance in the region. If you take the mean difference in the principal component time series, you can then look at how these modes of variability might trend in the future. And what we find is this across all models, so all these different dots are different models, we find a more negative NAO, most of them simulating a more positive East Atlantic pattern with the polarity shown as I have in the figures, and then a more positive Scandinavian pattern. So what that might mean then for the region of the British Isles, a negative NAO is generally associated with colder conditions, and the adjusted position of the jet stream leads to weaker and less frequent storms. So you get sort of this cold, calm, dry situation with the storms traveling, well south of the region that I'm considering. But a positive East Atlantic pattern would be warmer than average conditions and enhanced storminess and precipitation, in particular for southern England. And then a positive Scandinavian pattern gets these sort of anomalies. So generally cold. And then you have this sort of northwest southeast gradient in dryness and moisture. Right, so then what happens to the jet in these experiments? So these are the experiments that have daily output available on the left-hand side here. The black dot is the present day position of the jet, and then the arrow indicates where the jet shifts to. So you can see this general equatorward shift of the jet in the mean as well. What's not so clear is that what happens to the magnitude of the jet. So it doesn't necessarily weaken. There's all over the place across the models. It's on majority show weakening, but that's not necessarily a given. And we tried to look at how this correlated, how the model spread in these metrics correlated with the model spread in some of the large scale variability. And we found that the East Atlantic pattern was quite highly correlated with the spread in the jet magnitude. And I'll talk a little more about that later on. We do a Lagrangian tracking of storms, which allows us to have both this gridded output as well as being able to count every single track that goes within this box I've defined is within 5 degrees of the British Isles. You can see this is the response in number of storms that would cross the region. So you have an equatorward shift in the storm track, which is actually on average, if you count up all the storms, slightly negative due to the strong decrease just to the north of the region that overwhelms it. But as you can see, there's sort of very little response on average. So the mean is here just below. If you look at this distribution of the storms and how they'd shift, we have minus 0.12 storms per winter. So it's very small. It's a change of less than 1%. So it's basically meaningless. But the models are split 50-50. So you're kind of looking at this average that's coming out of that, whether they should increase the number of storms in the region or decrease them. You can get somewhat better understanding if you separate the tracks into 2 regions, one south of 54 degrees north and one to the north of that, where you have an increase in the number of storms to the south and a decrease to the north.
5 minutes left.
Pardon me?
5 minutes.
Okay, thank you. Yeah, but the large scale variability seemed to suggest that we'd have calmer conditions. So can we make sense of this in terms of looking back, looking at the intensity of the storms? So how does storm intensity change? I've now separated the tracks into those that exceed the 90th percentile of intensity, and that's the darker blue boxes, and those generally decrease everywhere. So we actually have a 10% decrease in the number of strong storms, which is much more significant. And the average storm intensity decreases across all the regions. And this is, so the intensity is well correlated with the NAO, so that makes sense. We can connect these things. whereas the number of tracks, which was poorly constrained across the models, correlates well with the East Atlantic pattern. Briefly look at precipitation extremes. They've the mean and extremes all follow this sort of pattern that looks like the positive Scandinavian pattern, where you have a dry kind of northwest and a moist kind of southeast. There's little statistical significance in this, and in particular, there's very poor agreement, which are the red dots, for kind of much of England. So we can't really say too much what would happen to precipitation under sea ice loss. Even when you separate by north and south, it's really no more clear. There's just too much model spread. We think that probably the storm tracks are really quite important for determining this pattern, and that we need to understand those a bit better to be able to understand this better. In terms of wind extremes, they're well correlated with these rain extremes, actually. So when we have our paper out, maybe you can look into that in a little more detail, but I won't go into it now. Right, so I showed you all that sea ice loss stuff. So what happens in response for the rest of the global warming experiment, over global warming, you actually have this almost opposite response. So this positive Scandinavian pattern, positive NAO, negative Scandinavian pattern, a more poleward jet, more storms crossing the region, and in particular, more strong storms. We see that something really similar for the precipitation and wind, where it increases across the region as a whole, where it would decrease in response to sea ice loss. So yeah, these things are sort of cancel each other out. One last thing before I talk a little bit more about these storylines is there's this idea that sea ice loss could lead to more extreme winters in terms of cold temperatures. So we looked into this a little bit, and what I'm showing here is how the magnitude of a 1 in 20 year minimum low would change in response to sea ice loss. Across the models, it's slightly positive, but there's a lot of model spread. That's what I'm showing here. We looked at a few different metrics of extremes. You can see it's level all over the place. But if you compare this to the response to SSTs, which I'm showing on the bottom, you can see this is statistically significant everywhere. There's a clear sign of the change. And if you look at the scales, they're about 10 times larger. So there's really no indication in these models that we'd have an increased risk of cold extremes for the British Isles under sea ice loss. Under general greenhouse warming. One tiny caveat to what I've just said is actually that the temperature response is correlated to the NAO across the models. And we know that the NAO forced response is underestimated by the models. So this effect might be slightly underestimated as well. It requires more research. So who wins the tug of war then? We have these alternate storylines. So we only looked at one storyline. That was this CMIP one, which had 2 degrees of surface warming and 3 million square kilometers of ice loss. So we test the ratio of 1.5 million square kilometers of ice loss per degree of warming. But what are the plausible ranges for this ratio? If we look at CMIP 6, and that's what I'm showing here, in time, the ratio of sea ice loss to global warming, the mean is 1.5 as expected. And you could have actually something as high as 3.5 times or as low as 0.25 times. And just to show you really quickly what difference that might mean, here is the net shift in the jet if you consider both sea ice loss and warming. The ratio simulated by CMIP is the dark purple in the middle, as a slight shift equatorward. If you had this high sea ice loss scenario, you'd have a strong decrease equatorward, shift equatorward. And if you had the scenario with very little sea ice loss, you'd have a shift poleward. You see something really similar with the NAO. So in summary, probably out of time, so I'll just quickly go through them, that we have this good agreement on the large scales, this really offset by the response to SSTs. It's not so clear what's happening with the cyclones other than they'd likely be weaker. We have a kind of gradient in precipitation that changes. We'd have generally weaker cyclones, which would also mean weaker winds and extreme winds. And the effect of cold on the cold extremes is probably too small to be relevant for climate change. So altogether, it means that the dynamical response to sea ice loss is probably quite important for projections in the region, and especially if there's more sea ice loss than occurs in the CMIP 6 mean. However, the thermodynamical response, like the changes to the temperatures of the region, is probably quite unimportant to understand. And finally, model spread in some of the metrics that had poor model agreement seem to be strongly related to the spread in the East Atlantic pattern and could potentially be used as a way to constrain projections. Thank you.
Stephanie, that's really interesting. Has anybody got any questions they want to ask Stephanie? about presentation? I don't see any hands up or anything in the chat as yet. I'll ask a question then from the, oh, wait a minute, and we've got a question from Lucas. Lucas, what's your question? Let's put his hand down, I think.
I think it was clapping.
Oh, okay. Well, I'll ask a layman's type question then. Looking at those results, I would be saying, okay, so there's nothing much to worry about then with regards to sea ice loss. If you like living in the UK, it's not a problem. But I'm sure it's much more subtle than that. So what's the next steps with what you like with your research? What you're going to look at next?
Me personally, I've just ended all my funding on this, so I probably won't be looking at anything more. Where I would think we need to look is probably more at constraining the responses to sea ice loss. So some of that spread was really quite large still, which kind of gives you meaningless conclusions. And so I think this potential to be using this jet magnitude or East Atlantic pattern to constrain some of the local changes. So we can kind of use these large scale things to constrain things at the weather scale. And that may be quite a useful avenue to go down.